to this second section of today. Kyrylo Simonov will present indefinite causality in quantum mechanics. Thank you.
Can you hear me?
Okay. Not at all. No, it's fine, no problem.
So, okay, does it work? Yeah, perfect. Okay, just maybe wait 2 minutes so everybody comes here.
More money in the court, more money. Every week, everything is money.
Oh, okay. Hello everybody. So my name is Kyrylo Simonov. I'm from Vienna, and what I would like to present to you today is a quick overview talk about indefinite causality in quantum mechanics and how we can use it in thermodynamics. So basically, first let me start with what I mean by indefinite causality in quantum mechanics. So we know that in standard quantum mechanics, we tacitly assume that there exists background time or a definite causal structure, in the sense that if I have two events in distinct space-time regions, so say Alice and Bob, we know that either one of the parties is in the past of another party, or they are space-like separated. But in quantum mechanics, actually, we know that the view of pre-existing values of observable, independent of the measurements, is actually problematic. Yeah? Due to, for example, Bell locality, Poppenspector contextuality, and other, let's say, other possible views. And so the question would be, what if causal relations are also a subject to the superposition principles? Basically, can we extend the observation that we know from quantum mechanics also to causal relations? 10 years ago, Oreshkov and Bruckner actually have shown that it's possible to go beyond definite causal structure and at the same time save the linear framework of quantum mechanics. So how actually can it be done? Basically, you can say that we abandon the global causal structure, and we say that the physical world actually can be modeled by local laboratories, which can receive as an input a quantum system, then perform some operations on the system, so which can be generally described by completely positive maps, and then send the system out of the laboratories. And then we say that, okay, inside the laboratories, the standard quantum mechanics is valid. But between the laboratories, there is no definite causal structure. And the causal relations between the parties can be encoded in the so-called process matrix. And the process matrix basically can be seen as a generalization of density matrix in which sense that, for example, if we have two local laboratories, so process matrix can actually completely defines the probability distribution of getting two outcomes, x and y, if we perform some operations n A and n B in these local laboratories, as I can see here. So, and interestingly, it's interesting that in this formalism, the process matrix does not necessarily, let's say, encode a definite causal orders between causal order between the events. And there can exist actually so-called non-separable process matrices, which cannot be separated into a convex combination of the process matrices which describe, let's say, definite causal orders of the events, say, for example, Alice before Bob, or Bob before Alice. And so in this case, we can say that such process matrices, they realize an indefinite causal order of the events. And basically, so what does it mean? So what is the outcome of such a formalism? So let me give here a simple example. So basically, we say that, okay, we have two parties, Alice and Bob, again, which play a game. So the sense of the game is that both parties, they receive random bits, A and B, and additionally to this, Bob generates a random bit, B prime, which actually defines who has to guess the bit of the other party. So basically, if B prime is 0, then Bob sends his bit to Alice, and Alice has to guess it. If B prime is 1, then we have vice versa situation that Bob has to guess the Alice's bit. So, and we can show that actually under, if the causal relations between the Alice and Bob are well defined, then the probability of winning the game can be bounded in such a way. So how can you actually see this? So for example, let's say that between Alice and Bob, we have a well-defined causal relation. And let's say that Alice is in the past of Bob, so in the past of Bob. So if Bob has to guess the Alice's bit, so then Alice can simply communicate this bit to Bob, and the task will be accomplished perfectly. But if Alice has to guess the Bob's bit, so she can do it at most randomly. And so in this case, we can calculate the maximum probability of winning the game under well-defined causal relations, and we will finish with such an equality, which is called a causal inequality, and can be seen as an analogy of Bell inequality for indefinite causal structures. And it's what is important that such a causal inequality, it can be in general violated by certain process matrices. So which means that by indefinite causality, we can outperform the strategies which use definite causality, basically. But now, so what the question is, so can we experimentally realize such process matrices? And actually, Giulio Chiribella with the colleagues have proposed in 2009 a particular indefinite causal structure, which is called quantum switch. And basically, the idea is that we can realize a superposition of causal orders of different operations. So, for example, if we have two operations performed on the system, N1 and N2, we can add actually another system, which in this case would be a qubit, and called control qubit, such that if the control qubit is initially in the state 1, yeah, then we realize the order N. So firstly we apply the operation N1 and then operation N2. If the control qubit is initially prepared in state 2, then we do the vice versa order. Yes, so firstly we apply N2 and N1. Okay, and in this case, so this means that actually if we prepare our control qubit in the superposition state, for example, plus state, then we can realize a superposition of causal orders of these two operations. And so it actually has been found that quantum switch can find so a lot of applications, actually practical applications in different fields of quantum mechanics. So, for example, in quantum computations, it can use to reduce the Corey complexity. In quantum communication, you can use it to reduce the noise of communication channels. In quantum information, you can quantify the incompatibility of unknown observables. And for example, in quantum metrology, you can use it for high precision of metrology of unknown channels. But actually, so what we are interested in today, so the question is, so what about thermodynamics? So can we actually use indefinite causality, and in this case the quantum switch, for a better performance of thermodynamic tasks? And the answer is yes, we can use it for a better performance of thermodynamic tasks. And so now let me quickly go through a couple of examples. So the first example will be the extraction of work. So basically, what do I mean by extraction of work? So let's say that we have a state, and we have a Hamiltonian for the system which stays in this state. And what we can do, we can actually vary these Hamiltonians in a cyclic way, which will generate a unitary transformation that decreases the energy of the state. And this difference in energy can be interpreted as actually work that can be performed on some another system. And also it is known that if we have a thermal state, so okay, if we have a thermal state which is a Gibbs, basically a Gibbs state, then no work can be extracted from this state in such a cyclic way. So also we can say that if we have two thermal reservoirs and apply them to the state of the system, the output state will be also a thermal state. So no work can be extracted from the output state in this case. So now, okay, let us consider this setup. We say that again. Initially, we have a thermal state at the temperature beta initial, and we apply two thermal reservoirs to the system, which are identical. They have basically the same temperature. So in this case, again, if we apply these reservoirs in a parallel way or in a consequent way, one reservoir and then another reservoir, the output state will be thermal state, a Gibbs state, and no work can be extracted from it. But surprisingly, if these reservoirs are applied using the quantum switch as a superposition, then the output state will not be always thermal. So you can, even if the initial state is thermal, you can extract some work from the output. And the second example, so it concerns the thermal devices. So basically, we can use the same setup as before, just adding one extra hot reservoir, and we can perform a three-step cycle using the quantum switch. So the first step will be basically applying quantum switch of cold reservoirs until we measure the quantum qubit. And if we measure the minus state, so in this case, the heat will be transferred from the cold reservoir to the hot reservoir. And basically, other two steps will be classical thermalization with the hot reservoir and then with the cold reservoir to get a complete cycle. And so basically, so the result here using the quantum switch will be the transfer of the heat from the cold reservoir to the hot reservoir, and we get, in this case, the refrigerator, which is boosted by indefinite causal order. And this is the proposal by Vlatko Vedral and David Felice. And actually, it's also interesting that such scheme can be even further improved if all the strokes, so each thermalization, are performed in a classical way, so in definite order. But they are actually boosted by generalized non-selective measurements, which are applied in indefinite causal orders by quantum switch. So this is the work by Pedro Rodriguez, which is also here. And it shows the power, let's say the possibility of building thermal devices with the quantum switch. So now the last slide, so going to the conclusions and the outlook. So basically, indefinite causal orders, they can be used as a resource in different tasks, so in different fields of the quantum science. So for example, as noisy communication and effective computation. And in thermodynamics, indefinite causal orders can be a resource to perform work and build effective thermal devices. But what I have to underline that the research on thermodynamics of quantum switch is just has begun. Yeah, and basically it focuses only on quantum switch, on the quantum switch setup. So the let's say the basic question which we have now to answer will be actually, can we explore indefinite causality as a valuable thermodynamic resource beyond the quantum switch, given just non-separable process matrices? So thank you very much.
Thank you for the interesting presentation. This quantum switch, does it already presuppose indefinite causal structures?
So do you mean that is it experimental realized already?
To build this quantum switch, are you presupposing that perhaps there are indefinite causal structures?
Yes, definitely.
Okay, so
but what is interesting about the quantum switch, which you still can realize in the framework given of standard quantum mechanics. So even you don't need the process matrix formalism to do it. So that's what is nice about the quantum switch.
I see, because like this process matrix formalism, it seems that once you write it down, it does not have any convexity properties, which the density matrix would have, and that would perhaps lead to some sort of missed out calculation or something which could give energy output, because
no, quantum switch cannot be written as a convex combination. So that's the difference, because convex combination, it means that you have basically a probabilistic mixture of the causal. So you have a coin, you toss in it, then you say if I have 0 I perform A and B, if I have 1 I perform B and A. So in the quantum switch you have a coherent superposition of the orders. So it cannot be written. It's like you have a density matrix, incoherent density matrix, and the same density matrix with off-diagonal elements, basically. So you can see this one as an analogy.
So you have a superposition of like what in your because if it's a superposition, it should be convex, right? Maybe I'm missing something. You can talk about it.
So let me. So basically, as you can see here, so it's in the quantum switch you can say that it's due to the fact that we have a coherent state of the control qubit. And since we have entanglement between the basis states of the control qubit and the orders, you can say that if we have coherence in the control qubit, it is equivalent to the coherence between the orders.
Okay, you can. Second question?
Yeah, I got a question about your work extraction with the two reservoirs. After the work is extracted, are they both at the same temperature, or could one of them be higher than the other?
You mean the reservoirs?
Yeah, after the work has been extracted. Are they both at a lower temperature or at the same lower temperature, or can they be at different lower temperatures? What would happen if one of them, if they weren't identical? One of them had a higher heat capacity than the other.
Yeah, I mean the point is that you have like two different steps. You have the thermalization with the reservoirs,
right.
And then you forget about the reservoirs. You get some state after the quantum switch, after the reservoirs, and you extract work by applying unitary cycle to it. But this applying unitary cycle has nothing to do with, let's say, with the quantum switch. So you don't after the quantum switch you don't care at all about the
maybe it would be interesting just to see what would happen to them after.
No, nothing at all.
Okay, so let's thank the speaker again.
Thank you.